We are going to start talking about electrical stim, and it is divided into two modules. This week's module is basically going to be the introduction to electrical currents. The text reference for this module is chapter 11. I have got it arranged a little bit differently from how it is in the chapter, really in an effort to make it more understandable. The material for electrical stim, there's a lot of it. It's pretty technical and it's very front-loaded. In other words, we're going to talk about all of the lecture material before we ever get into lab and get to practice it. So sometimes it can just be swimming around in your head with all that information because you haven't had a chance to do the hands-on part. So I'm going to try to make it as understandable as possible, so then when we do get into the lab, it will make sense to you, I'm hoping, and we will get it done. So as some of you work in as aides in clinics, and you have applied IFC or some form of electrical stim to patients, and so you're somewhat familiar with the application part of it. The difference between a PT and a PTA applying electrical stim to a patient and an aide doing it is that a PT and a PTA need to know the background information. We need to know, how do we adjust the parameters to get the clinical effects that we need, and how do we assess whether or not we're getting the clinical effects that we need. That's the difference between electrical stim being a skilled therapy and an unskilled therapy. So that is a pretty important distinction, and we're going to talk about that with a lot of the different therapeutic interventions that we learn in this program, is what is skilled therapy and what is not. Because you can bill for skilled therapy, but you cannot bill for unskilled therapy. So we are going to start out talking about some terminology, just basic electrical terminology, and then we're going to talk about individual waveforms and contraindications, indications, precautions, just like we do with all the other physical agents that we're talking about. So the learning objectives for this section are to define the following terminology: current, charge, voltage, conductivity, polarity, resistance, capacitance, and impedance. I want you to be able to state Ohm's Law and its application to current flow. Basically, Ohm's Law talks about how voltage and resistance affect current flow. Okay? I want you to be familiar with the physiological properties of excitable tissue, and when we're talking about excitable tissue, we're talking about nerves and muscles. I want you to be able to define action potential, threshold, refractory period, and accommodation. Okay, we'll talk about all these. So electrical current is the flow of charged particles, and we know that in the body, the charged particles are electrons attached to ions usually. The speed of electron flow is measured in amperes. And this is whether you're in a biological system or a non-biological system. Therapeutic current flow is measured in milliamps and microamps. So that's 1,000th of an amp or 1,000,000th of an amp. So really tiny charges. But it works in the body. You can think of electrical current, the flow of charge, as being analogous to the flow of water, like water running in a pipe or a hose. Charge, in and of itself, is an imbalance in electricity in the body. So it's an excess or deficiency of electrons. And in our body, it's carried by electrolytes, dissolved ions, sodium, potassium chloride, calcium. We talked about this we talked about electrolyte and fluid balance in pathophysiology last quarter, and that's why it's important, because those are our charge-carrying ions. Charge is expressed in coulombs, which is the quantity of electrical charge. We don't really need to know that for electrical stim, but just FYI. Any substance that allows the passage of charged particles is considered electrically conductive. So voltage is stored charge, and voltage drives current flow. So you have to have stored charge In other words, an excess of electrons somewhere in order to have current flow. And so it's analogous to a water spigot controlling the water flow. If you have more voltage, you're going to have more current flow. If the spigot is on more, you're going to have more water flow. So conductivity is a material's ability to propagate current. So there are things in the body and in nature that are electrically conductive and things that aren't, or more or less conductive. And so if something can propagate a current, it is electrically conductive. So nerves and muscles are electrically conductive. Fluids, water particularly, is electrically conductive. And then we have other things in the body which are not. Polarity is the property of having two oppositely charged conductors, an anode, which is positive, and a cathode, which is negative. In a conductor, free electrons move from negative to positive because electrons are negative and they get driven away from the negative electrode to the positive electrode. So like charges repel and unlike charges attract. So resistance is the opposition to the flow of charged particles. So resistance increases in the cross-sectional area of a conductor decreases as the cross-sectional area decreases. So if you think of it as a hose, if you have a skinnier hose, you're going to have more resistance. Resistance also increases as the length of the conductor increases. So you're going to have more resistance in a longer hose than in a shorter hose, if you want to think of it that way. Capacitance is the ability to store charge in an electrical field and oppose a change in current flow. So a capacitor is two conductors separated by an insulator. In a biological system, electrodes and nerves are conductors, and skin and fat are insulators. So our phospholipid membrane in the cell, it has the water insoluble part, the fat on the outside, and the conductive part on the inside. So we have a built-in capacitor in the cell. We have the ability to store charge so we can create voltage and create electrical impulses in the body, which is pretty cool. So basically, we use that system to transduce sensations and physical things into electrical impulses that the brain and nervous system can understand. So if we didn't have that ability to store charge, we wouldn't be able to do it. That's what makes things work in our nervous system. And we'll talk more about this in neuro next quarter as well. I think it's pretty amazing we can do that with some biological molecules. Impedance is the opposition to current flow in biological tissue. So you can think about impedance as being a combination of resistance and capacitance. It's frequency dependent and it's measured in ohms, just like resistance is, because it's biological resistance. So there are some things in the body that are conductors, like muscle and body water. So just our body fluids. Electricity flows easy through these conductors. Resistance is low and impedance is low. Fat is an insulator. Electricity does not flow easily through it. Resistance is high and impedance is high. So we have that opposition to current flow. And you've probably seen, or I don't know if you've seen, but they have body fat testers where you hold on to two electrodes on either side, and it measures basically the resistance of the current through your body, and that's how it determines how much fat you have in your body. Because muscle and body water are conductors, and fat is an insulator. If you have more fat, it's going to have a slower current because you have more impedance. That's how those impedance body fat detectors work. Of course, the gold standard for body fat measuring is hydrostatic weighing, but you'll see those impedance units are smaller and easier to use and less expensive, so you'll see those used as well. So Ohm's Law, it's a description of how current is affected by voltage and resistance. So current is directly proportional to voltage and indirectly proportional to resistance. So as voltage goes up, current goes up. As resistance goes up, current goes down. You can also think of it as voltage equals current times resistance. So you can arrange it either way. So the little graphic, it's current is Tesla equals volta over ohm. So current equals voltage over resistance. Kind of silly, but there you go. So an action potential in the body is sort of the nerve stimulation. It's a rapid sequential depolarization and repolarization of a nerve that occurs in response to a stimulus, and it transmits along the axon. The action potential is the message unit of our nervous system. So the threshold is the critical membrane voltage that's necessary to alter those membrane ion channels, make the membrane more permeable, and generate an action potential. So the action potential occurs in a nerve when its threshold voltage is reached. So the threshold, it's sort of an all or nothing response. When you get to that threshold, the action potential fires, bam, it's on the way. It's headed down the neuron. If you stimulate a neuron below threshold, it will not fire. Okay, so you have to have at least that amount. So once the action potential is generated, it triggers the action potential in adjacent areas of the nerve membrane, and that's how it propagates down the nerve. So we'll talk about this in gory detail in neuro next quarter, but just know that you have to have a critical amount of voltage to depolarize the neuron enough to propagate that action potential. If you have below threshold, it's not going to work. There is a period of time which is known as the refractory period, when a cell is either impossible or way more difficult to depolarize, either physiologically, so your brain sending a signal, or electrically using an electrical stimulator externally to do it. So the refractory period, the absolute refractory period is when you just cannot repolarize a cell. It's impossible. The ion channels are not cooperating with you. And the relative refractory period is when it's just going to take more electricity to do it. Accommodation is an elevation in threshold that occurs when a cell has been exposed to a gradually increasing stimulus, but it never reaches its critical excitatory level required to generate an action potential. So nerve cells accommodate way more than muscle cells. Nerve cells are much more likely to accommodate than muscle cells are. So action potentials usually, they travel faster in large diameter myelinated nerves than in small diameter unmyelinated nerves. And we will talk more about that, certainly. So electrical currents are used clinically because they can stimulate action potentials in sensory and or motor nerves. So that's the reason why we can use them, because you can use them to stimulate an action potential. It's kind of neat that you can do that. So in the next section, we're going to start talking about waveforms and parameters and how those combine to stimulate that action potential.